Well, good morning and welcome to Cosmic Conversations here on the Morrison Planetarium Facebook page. My name is Ryan White. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences. And I'm joined today by Jackie Faherty, Senior Scientist and Educator at the American Museum of Natural History in New York City. So a little East Coast meets left coast this morning. To talk about an amazing instrument called the Gaia spacecraft. So welcome, Jackie.
Thank you, Ryan. Thanks for having me. It's always fun to chat on these things and use awesome visualization tools to fly around data.
Absolutely. And thanks. Congratulations too. You are the only two-time Cosmic Conversation guest that we have had here. So thank you for joining us once again to talk about a completely different topic. And we initially talked about brown dwarfs way back in May, but we're going to be talking about the Gaia spacecraft and data set, which can't think of anyone better to talk to about than you. So we're starting with a view of the Gaia spacecraft, and then we can just kind of go from there.
Yeah, so as you know, I love this thing. This is a telescope in space. We're kind of orbiting out where it is. It's 1 million miles away from us right now. It's at a stable point in the Earth-Sun orbit. It's called a Lagrange point, and it's Lagrange point number 2, or L2. And it can exist out there and remain very stable in a nice dark area of the no atmosphere to worry about from Earth. It can keep that shield against the sun, so the sun's not a problem for it. And what it's been doing very carefully and precisely is scanning the entire sky, all 360 degrees around it, and measuring the position of every single star it can see. And it does it many times. It's been in orbit for several years now, 4 years now. I think 2011 is when it was launched, somewhere around then. And as it's been doing that, it's able to watch so precise, the most precise thing we've ever launched. And it's been cataloging exactly where the stars are. It has revealed the positions, the distances, and the motions, how fast stars are moving, for roughly 1.7 billion stars. That's unprecedented to have something do that.
So like right now, we're just showing sort of what a kind of naturalistic-ish view of the sky would be. And we're using a data set of about 100,000 stars, but I can go ahead and replace those with kind of an artificially brightened version of the Gaia data set.
Yeah, this is not even a fraction of the stars, right? Like this data set that you just turned on is a subset of that 1.7 billion. This subset is actually 8 million stars, and we can only see a fraction of them here because you've brightened them up, as you say, arbitrarily. We've made them a little bit brighter. They're all there. All these stars are there. You can't see them because our eyes are not susceptible to seeing them. And they're there. And don't you want to know who's in your neighborhood? I always say that to people. Like, don't you want to know what's in your neighborhood? Don't you want to know who's around? Yeah, that was Mr. Rogers. Wasn't that Mr. Rogers?
That was.
It totally applies to astronomy. Yeah, very Space Odyssey kind of moment, right? Like all those stars. And something that you can do, Ryan, if we kind of pause the natural rotation here.
Sure.
So the other thing to notice here is that I know you love looking at colors with your lovely affection for certain colors. The colors both you can see and then you cannot see. But these are color-coded by temperature. So, the redder stars are the fainter stars, and the yellower stars are the brighter star, or the warmer stars. And so this is also giving you some info. But we can show what it would look like over time. Do you feel ready to do that, Ryan?
I can flip the switch for that. How fast do you want to go?
Let's take time. So we're kind of like, pretend that we're sitting on Earth, right? what we are. And this is like staring at some view of the sky. I'm not actually sure what area of the sky this is because we don't have bright stars in Gaia because they saturate the detector. So it's like a weird nighttime sky view that we have right here. But we are looking at an area of the sky right now. It looks like we're kind of staring at a bit of the Milky Way on the bottom left-hand corner.
Could cheat a little bit and show like our Hipparchus star set here. Oh, it looks like actually we're looking at Alpha and Beta Centauri.
Yeah.
Southern Cross. Ooh.
There we go.
So
we were looking at the Milky Way there. Yeah, that's a good cheat.
And so the patterns that people have looked up to the sky to see for thousands of years, I mean, basically haven't changed. So the perspective of the kind of the human experience of the sky is that the constellations never change. And yet what Gaia is showing us is that, in fact, all of this is in motion.
Yeah. So you can take time and let's see what things look like forward in time. So let's set time to 50,000 years a second.
Okay, I have 30,000 years a second I can do.
Oh, do 30,000. Yeah. We don't want to go too crazy, I guess. And then once you hit go, what we're going to see is something that none of us will ever be able to see because we don't live for long enough, but the universe is way older than we are. So
I'm actually not seeing time moving forward. Let me try. I'm going to really fast forward. So I'm going to put it at 500,000 years a second.
Oh, yeah. You may have to do 500,000. Nope. There is, I should say, 50,000 should work for this. Are you, if you hit F1 maybe and look at the native GUI and see what it says?
Sure.
You might be able to do the regular drop-down menu. Yeah. And then change it from seconds per second. It looks like it's in seconds per second down there on the bottom to the right.
Oh, yeah.
Up a little. This feels like a game of hotter, colder.
So that's at 1 hour per second?
Well, if you look up, there's the drop-down menu that you should be able to just swap it to.
Thank you. So now is the time where I guess I should admit that this is my first time live piloting for a program using OpenSpace. So.
And then click resume. And I should say I fly this thing by myself at home a lot, but I always love having a pilot because it's a lot easier. There we go. Okay. So now what we're seeing is the changing nighttime sky, right?
Yes.
It's beautiful. So now we've sped it up so much it's slowed down. I think you might have put it at 500,000 at this point because they flew apart really fast.
I think so. So let's try that again.
Let's try that again.
See if I can do that. Yep.
And as you're setting it up, I'll just say what we're doing is this really cool thing, which is exposing everyone to the dynamic nature of our local area in the Milky Way. Since what you're able to see here is motions that are going on right now. Like these stars move at very rapid paces, 20 to 30. How do I translate that? What is kilometers to miles? Is it divide by 1.6?
Divide by 1.6.
Let's just say that these stars move at like 30 miles a second. That's fast.
That's fast.
You know? So like that's how they move through the galaxy. And we've just fast forwarded for you to show you what they would look like. It's like caravanning and they're going around the Milky Way. We're doing it too, but we've removed that motion from this perspective so that we're seeing it as if, you know, our motion has been removed and these are what the other stars are relative to us. So
it's not like we're on the merry-go-round riding with them. We're just watching them speed by.
Right. We're watching them speed by. So, and here's what's critical and key is that we use this information to figure all sorts of things out about where stars are going, where they came from, how they formed, who they formed with, like family members, like who's traveling with who in the galaxy, is really, really important for us to tell the full story. Because don't you kind of want to know, like, how many stars did we form with? Like, where's the stars' brothers and sisters, right?
Right, our siblings, yeah.
Yeah, where are they?
Well, the other cool thing is that we're seeing this sort of in 2 dimensions, but in fact, the stars are moving in 3 dimensions, and so that's an even added kind of layer of complexity on all this too.
Yes, that's right. And actually, this data set here is a specific data set that we've chosen because Gaia, the observatory that's out there at 1,000,000 miles that we started this whole program around, with the viewpoint of, this is a subset for which it measured both the 2-dimensional motion of the stars, meaning kind of like the projected, as well as that 3rd dimension of towards or away from us.
Very cool.
Because that's actually a really important motion. One thing, a little tidbit I wanted to share is that this is actually a scientific thing that I'm pursuing. And people at home can do this by looking at the Gaia data sets themselves. If you find a star that's really close to us, like big parallax, what we call, which is what Gaia did, it's a parallax mission. It measured the shift in the sky that these stars wobble back and forth because they're close enough that we can see it when we move around the sun. If you find one that's really close and it has basically 0 proper motion, or 0 of this translational motion that we're looking at here,
right.
It may very well be that it's either careening towards us or away from us. So you could look for that. Actually, I keep meaning to do it. It's on my to-do list that I don't think anybody else has done it yet, for the lowest mass objects. Somebody did it for this sample, which has radial velocities or the motion towards or away from us, but there are only 8 million of those within the data set. And there's 1.7 billion stars, right? So, and speaking of which, I feel like we could turn on another data set. Are you ready to maybe show another one?
Sure. I'll go back to the present here, first of all. And then, which data set would you like to look at?
Let's turn on the M dwarfs, because those are very prevalent near us.
Okay.
Okay, yes, perfect. So the reason why it looks funny is you can even brighten them a little, Ryan, like we could luminosity them up.
Sure.
So this is a specific data set that actually my grad student worked on. I have another data set in there called Gaia M dwarfs. We'll turn that one on next. But right now, this one are all of these objects. They're called M-type stars that we have spectra for. So we've actually taken like a prism, we've put it on the star, and we've taken their light, we've figured out what they are. So every one of these has been what we call spectroscopically characterized. There's 70,000 of them. And the reason why it's a weird pattern that you'll see as we like brighten them up a bit is because they were all... Yeah, okay. They don't seem to be brightening. Interesting. Is that the Gaia M dwarfs one or the regular M dwarfs one that or the M dwarfs? There's 2 data sets in there. One's called M dwarfs and the other is called Gaia M dwarfs. That might have. Oh, that was the wrong one. Yeah. So if we go to under Gaia drop down, so if you open that up.
Got it.
Yeah, and now we can.
This is great. You're also getting an introduction to how to use.
This is OpenSpace, so people at home can do this too. Yeah, there we go. So the reason why it looks funny here is because all of these were observed with the Sloan Digital Sky Telescope. Sloan Digital Sky Survey, and so they have a funny pattern on the sky because it was all of the views that one might see. Natalie Loyola Diaz, whose second comment here is that OpenSpace. Yes, this is all OpenSpace. And Ryan is giving you a masterclass tutorial a little bit because he's opened up the hood and is showing you how you can play with some of the knobs and digits and whatnot of this.
Yes. The part that we often try to conceal, but sometimes we allow the peek under the hood.
You can see them. They're cool. Well, let's see. So
basically, you're saying that like the Sloan Digital Sky Survey, like Gaia covered the entire sky. Sloan only covered part of the sky. So what we're seeing is the intersection of where Sloan and Gaia intersect, basically.
Exactly. Yeah. So this is Sloan matched to Gaia. And it kind of runs out at a certain point because the Sloan Digital Sky Survey is a telescope in the north, not the south. Mm-hmm. So you basically get the southern. But there's another data set. Let's see if we can find it under the hood again. I think it should be in there. We did not test this beforehand, but I'm pretty sure it's there. That it's another M dwarfs. So this is just Sloan Digital Sky Survey, but then I put in the 100 parsec Gaia M dwarfs.
We have that indeed. So,
okay. And the reason why I want to show that, okay, cool. So this is, again, just a subset, but these are the most prevalent stars in the galaxy. They're so like our sun is not the most common kind of star that you find if you look in all directions in the Milky Way. These stars, these M dwarfs that are now mapped for you three-dimensionally, are the most common stars. If you pull away, we can see the bulk density that we have of them.
Little change, so we can do that.
Close to the.
I'm going to put the sun in our center of our field of view and now pull away.
Nice.
Far enough away from the sun that we start to see the relative distances between the stars.
So I made this data set for a specific reason, which is not necessarily relevant to go too far into. It's for a talk. And I wanted to show off some of the artifacts that Gaia has. And so if you look at the Milky Way, that's kind of at the bottom left corner of the screen right now, that's actually artifacts that you're seeing in the Gaia data. So you see there's like stripes that it looks like it takes out of the center in the like large stream. That's just Gaia problems, actually. And sometimes that's really important to dig into. Those aren't necessarily real sources. You have to clean all that up. But this is, the M dwarfs are everywhere in all directions. Everywhere that you look, you will find an M dwarf. M dwarfs are pesky little things in all directions. And I've cut it off. I only did a little volume for you here. This is the 100 parsecs volume. And you see how it looks like, so this is like inside baseball kind of thing. But do you see that shape that's there?
So this one?
Yeah. So that is a Gaia problem. That's actually the plane of the Milky Way, which clearly does not exist within 300 light years of the sun.
Right. Yeah, exactly.
But you can see it really well here. This is a Gaia. Gaia gets confused when it's a really crowded region. Mm-hmm. And so you're seeing a signature of that confusion that you have to clean up. But I love it. Look how that's so clearly visualized here.
Yeah. And we actually still have the Milky Way kind of in the background. So as we sort of orbit around, you'll be able to see how this like projects onto where the Milky Way is seen from Earth.
Yeah, when we come back around, that'll look really good. You know, I had colleagues that were playing with that part of the data, thinking that they were looking at real things. And all you have to do is pop it into OpenSpace or any 3D visualization tool, and you can see right away, like, boom, you're looking at a problem in the data, not real sources.
Well, that's a really good point, too, that these visualization tools, I mean, we like to use this on our programs for sharing astronomy discoveries and that. But I think one of the great things that you do is being engaged with how to use these for research and being able to reveal things like this. Things that wouldn't be obvious if you're just looking at a big, giant like spreadsheet of numbers. But when you visualize the data, become just readily apparent.
Yeah. I mean, as you know, I really love using these tools for scientific research as much as I love using them for educational stories. But I feel like we should get to the really fun sci-fi story that we can tell with the data.
So should I head back in toward the sun?
Yeah. Let's go back home. And as we do, I'll tell you, this is a project that I've been working on with Lisa Kaltenegger, who's an astronomer at Cornell, which is Ryan's alma mater. So I feel like that's a shout out to Cornell. Well done. And a recent paper just came out by Lisa and an astronomer at Lehigh University, Josh Pepper, which looked at the stars that are in Gaia. So mapped in Gaia using the velocities of Gaia, the precision of like exactly where they are of Gaia, that from their position, they can see the Earth transit the sun. And I feel like we should do the explanatory thing about transiting since you've got that queued up anyway, Brian.
Oh, yeah, that would be great. So we're coming back here on the solar system, and I guess we'll get to that in a moment. But the important point is that our solar system is all of orbits of the planets are pretty much in the same plane. And that becomes important when we think about how some of these transits are visible. But I think, we could cue that transit video and talk about how what it looks like when a planet passes between us and its parent star.
We've got it up. And so this is a perspective of you staring at a planet pass in front of the star that you're trying to look at. You don't actually ever see the planet. We've got it so that you could see it as if you were close to it in that visual. But instead, you stare at the light of the star and you watch the light dim ever so slightly, depending on the size of the planet and how close it is to the star. So that's what the bottom graphic is showing you. The light of the star will dim. And this is the most successful, as far as numbers goes, method that we've had at detecting exoplanets around other stars. So stare at every one of the stars that we've got up there. You know, we showed you all those stars that Gaia has, and you can stare at all of them. And if you have the right orientation, like Ryan's flying around here, our solar system, you have to be looking at it from the right angle. Too far up, too far down, too far to one side. And you're not going to see it. You're just going to have like an off angle and you won't be able to see it. So there's only a fraction of stars that we can see it for. And the paper that just came out, which had a really nice press release out of SETI, the Search for Extraterrestrial Intelligence, and Cornell Institute at Carl Sagan. It's a Carl Sagan Institute at Cornell. What it looked at was the stars that can see us, the Earth, transit in front of our sun. And you can put that data set up, Ryan, it's a specific subset of Gaia. Yeah, cool. I love this.
It's very cool.
See how thin an area that is? That's a very thin area.
So these are the ones that can currently look at us and see what's going on.
That's right. So those are the ones that could stare towards our sun and see us block the light of our star for it takes us 365 days to go around. So you'd have to be watching us for a while. But from their current perspectives, if they looked at us at the right time of the year, from their perspective, they're at the right angle, and we will pass in front of the sun and cause the light of it to dim. So what's interesting, right? Like this is, if you pull away, and let's show the three-dimensional structure of those stars, since from this perspective, it just kind of looks like a flat view around us. But as we pull away, you start to see, we'll see that it's like a disk of stars that goes out. And a key thing is that this selection was limited to those that were in roughly, I think, like 500 light years or so. And so we can kind of move around them.
Stars here, so we get a better look.
Yeah, there's some Hipparcos stars that floated in. You'll see it's like a disk of stars in space that we can see. Yes,
so
for Julieta,
like the plane of our solar system and just extended it out into space in a way.
It's even more specific than that, which I didn't appreciate. It's the plane of the Earth. Because Mars' plane is a little different, so is Jupiter's. And you can brighten them up.
Brighten these up.
Yeah, let's brighten them up. And when you do, like this is a question for your audience, maybe, if they want to give their answers. So these are the stars that can see us right now. Take a vote. Would you rather scream at these stars and say, hey, look at us, look at us, look at us. Like, make it clear we're here. Like, pick one. There's 3 in here that are actually known to be exoplanet host stars. Like, they have planets around them. Or would you rather cloak the Earth so that they can't see us? Because dark forest theory, you know.
Yeah, because maybe they're going to come and steal your stuff.
Yes.
Which
one would you rather, Ryan? Which one would you rather? Beam out to them?
I'm putting you on this spot. I mean, I guess I've always been a more optimistic kind of person. So my gut feeling is that we should be able to broadcast our location out into the universe, and that, I mean, we're kind of doing it anyway, maybe not quite this far, because our radio signals leak out of our ionosphere, and so we've already let anyone who's paying attention know that we're here. So part of it is kind of like it's too late anyway, but also, I am generally optimistic, kind of the Carl Sagan school of friendly aliens. So I would say that I'm not so worried about it. But then the challenge is that it's like, the stakes are so high because it's about our survival of our civilization, our species, our planet. So that makes it maybe a little trickier.
Yeah.
And what camp do you reside in?
It depends on the day, I think.
Yeah.
At this point in time, I think I'm more of the camp that it's very dangerous to expose yourself, or at least the unknowns are what scare me the most. And so I am fearful of an open invitation to the galaxy. And just as a reminder, these are our neighbors, interstellar wise. Like, these are the stars that, from their consideration, and actually, if you pull away and we can show like the whole galaxy from here, it really puts it into perspective how close these things really are to us. Like, speaking of intelligent species that might be out there that have the ability to do interstellar travel, like, that amount of space to them, if they can move around the Milky Way or even like move between galaxies, that's nothing, right? Like, that's basically inside of your house. And so
super bright there for that disk.
Yeah, I mean, check that out. Those are, if there is, the other aspect of this is, if there is intelligent life there and they've really figured it out, whether we scream or not, they found us. Mm-hmm. Like, we have so many obvious signatures of life that we've been beaming on, not even just, like our transmission signals, but the signature of biosignatures in our atmosphere. You don't have to look too hard, and you can see a good civilization could probably see that we're on our way to some pretty bad things that we're doing to our atmosphere for habitability of the carbon species that we are, right? Like, I don't think that we can hide, but I do fear that I'm not as excited about screaming like, let's do this, aliens.
So you're not joining METI anytime soon, the Messaging Extraterrestrial Intelligence Institute.
Yeah, I had the SETI stuff on my laptop when I was in college. I loved it. I thought it was a super cool idea, and I'm such a different person now. Like, I've grown so much.
Yeah, well, a couple administrations between us then and us now, so
that's true. So the other thing is, these are, and actually don't know how much more time we have. If we
got a little bit more time. Actually, what is this gap in the data here that makes it kind of look like a Pac-Man?
I noticed that as well, and I'm not sure what that is. I didn't collect this data. This came from Lisa and Josh. And it's only when I plotted it in 3 dimensions that I noticed that. And I've been trying to figure out why there is that, if there's something in the data. Like, if you keep moving around, we can do real-time science and see if it lines up with any crowded area. Because I don't think that
so should I put up the other Gaia stars as well then?
Yeah, you could. And we could see if there's and there's no gap there. well, you could lump them down and then see, but then we're really doing science as we go, because there's other things you can do in OpenSpace that's cool. Like we could cut it to the same volume of data, and then we can cut on various parameters that are in the Gaia data set to try and figure out what it might be.
That's good.
I think this is also matched to TESS observing test targets. It could be something with the TESS data set. TESS is the new NASA mission that's in space called the, oh my gosh, I always mess it up. Transiting
Exoplanet Survey something?
Yeah, what are the two S's? Transiting Exoplanets, I don't remember. Somebody look it up and then put it in the chat, and then we'll feel good about ourselves. But the thing about those stars that we were just looking at were that they were a snapshot in time looking at us.
Right. So if we put those back up, actually.
Yeah, if you put them back up, and now let's just make them move. Oh, that's it. Transiting Exoplanet Survey Satellite.
Survey satellite, okay.
Survey satellite. So now this little given collection, does that have the gap in it? Have we lined up with the gap there?
I think that's pretty much where the gap is.
Yeah, there's like teeth marks taken out of one side and the other.
Yeah, because the rest of it is pretty crowded.
Right, it's pretty well mapped across.
Yeah.
And it does.
There's Kitty making her cameo.
Oh, I hear Kitty.
Yeah, that would be my cat.
It's a good cat.
Yes.
Here's the other idea for people that I like this kind of cool take on, these are the stars that might see us, and let's fantasize about the equivalent best of like our planet that have the best intentions and want to go and like just talk to each other as however we could communicate and like say, what do you think the meaning of life is? Well, here's what we kind of think. And that would be really cool, right? And like we could study their biology and blah, blah, blah. But more than likely there's pathogens that we don't want to be exposed to, a virus,
right.
that kind of thing, That could be quite dangerous.
That microscopic life, not just the intelligent life, right?
Yeah, it could, right? Like we don't know. This has been the story as old as humans' time, that as we move from one place on the planet to another and you get exposed to areas that you haven't been in before, you're susceptible to pathogens that didn't make you sick where you were.
Right.
So it's a danger. Like viruses are a super danger, and we wouldn't want that. But those worlds are just the ones that we would see transiting, and likely if something is going to be so extreme that they could come visit us, they totally have the ability to like image us. They don't need to just see us transit. Right. They're going to have an extremely large telescope or some James Webb Space Telescope on fire kind of thing in space that could directly image us and like probably see our continents kind of thing.
Right. Or at least be able to look at the increasing CO2 levels that started with the Industrial Revolution and say, they're heading for something crazy in the next 100 years or so.
So I like the idea that there's like an alien species out there that's doing PhDs on watching other civilizations like destroy themselves or whatever. And we're at that like weird phase where this is when climate change usually happens. And we can go one of 4 routes that the aliens have seen other generations of these intelligent species go. Like we're either going to screw this up, or we make the right change and we go and, and so all they do is watch, and they're studying like what phase of the problem you make it to. And
writing academic papers and getting tenure.
Yeah, for aliens. Yeah.
All right. Well, thanks for a tantalizing talk this morning. I don't know if we have any other questions coming through, but if not, well, actually, we do have a question. So, effects of scintillation when a broadcast transmission is sent over a couple hundred parsecs.
Ooh. I don't know how to answer that. Meaning, I think maybe Steve means that does the signal degrade as it gets farther away?
Right.
Perhaps.
One of the tricky things is that it's not like aliens would be watching I Love Lucy or something. The radio transmissions that escape from our ionosphere are really only the strongest component, which is typically the carrier wave for something like a television broadcast. And then things like radar and actually atomic explosions when we did above ground nuclear tests. So it's kind of a weird subset of human technology that makes it through if you're looking at radio emissions. So
I was going to say one thing that I always thought was interesting is there's a lot of that is we're accidentally transmitting. We're not succinctly like sending signals out. SETI has made a different attempt at this than say like you say a chemical explosion, something we did here that sent off this one-time signal that if somebody were listening might have caught a glimpse of, or I shouldn't say listening, it's really watching because it's electromagnetic radiation. But if we wanted to be smart about it, which is the things that we think maybe aliens would do, we would send a distinct signal at a wavelength that we know that everybody would be looking at. So, for instance, hydrogen has a very clear signal across the universe because of what molecular gas does at 21 centimeters. And what we would try and do if we wanted to like really beam out a like, hey, we're here, you would beam at a frequency that everybody looks at. Any alien civilization would be looking at 21 centimeter line of hydrogen because it's everywhere in all directions. It tells you about that epic of various aspects of the history of the Milky Way. So you would send that signal at a frequency and you would like do it Morse code type thing where it's clearly not coming from some cool hydrogen molecular gas somewhere.
Or pulsar or some other thing. Yeah.
Right. Yeah. You have to make sure like it's clearly artificial in nature.
Right.
And actually, just as an aside, there's something called the WOW signal. You know about the WOW signal, right, Ryan? Yeah. So
we posted about it on Facebook if you look at our.
Oh, did you?
We posted about it a couple times. Yeah.
Did you post about the most recent survey that came out about they checked it with Gaia stars?
No.
If you set up the WOW, I don't know if we have time to do this, but if you set up real quick the WOW signal, I can tell you the new thing with it.
All right. Is there something in OpenSpace with that?
No, I don't mean that. I mean just tell the story of what the WOW signal is.
Tell the story of the what year was it? 73 something?
70s, I don't know.
Yeah. So there was a signal that didn't match what we expected for a radio signal. That didn't match what we expected from a natural phenomenon, but was never it never correlated with never repeated, and it never. Oh, here we go.
Josh got it.
Yes. So Josh is our behind the scenes producer, and Josh pulled up the image just in time to show what was circled on a printout back when printouts were used, and it merited someone writing "wow" in the margins of the printout.
And for a really long time, this is a classic. Like you would be looking with a radio dish, and you're trying to figure out this is just like the standard way of analyzing a signal at that time. But that little tidbit that was circled is not normal for that area of electromagnetic spectrum. And so it's circled called WOW. It's very famously called the WOW signal. And what some researchers, I think this was a paper that came out last week, week before, where while it was WOW, because it's like, is that aliens? Did we just find?
Right. Oh no, we're losing you at a really bad time.
Was that me, or was that I lost you there? Am I still back?
I think we lost each other, but yes, you're back now.
Okay, I'm back. Well, it was a WOW Like, is that this exact thing? Like an alien sending a signal, I'm here, I'm here, I'm here. And astronomers tried to find explanations across every phenomenon for it and couldn't find it as a systematic, and it remains one of these things that's kind of strange. And 2 weeks ago, a paper came out, I don't know if it was 2 weeks ago, it might have been last week, that looked at all of the F and G stars in Gaia that lined up with where that signal might have been coming from, as kind of like a thought exercise, as if it was going to come from a civilization, these might be the stars it could have emerged from. So more evidence of Gaia connecting to the kinds of things. I mean, Gaia can handle anything and everything, but if you want to know where things are, how they might connect to something another astrophysical phenomenon, you need to look towards this catalog. And I thought that was a cool one, because I was like, wow, signal.
Really
We never, it was an interesting use of it.
Well, before we wrap up, actually, did you want to talk, because I don't think we touched on this, or the next generation of the neighbors that can see us, which is sort of the changing over time. Did you want to talk about that before we head out?
I'll just mention very quickly, because that's a paper in the works that Lisa Kaltnager and I are working on, which is there is the stars that can see us statically right now, meaning like,
you can put that up like that.
Oh, perfect. Yeah. So that's a moment in time, though. And so the next question you might have is, how long can they see us for? Because we started this whole discussion with showing you all of those stars in motion. And so that's the new work that we're doing. And it is super enhanced by these visualization tools, because I can turn time up and watch them moving. And you can see how many stars come through and then leave our transit viewing zone. So if they're like us, like our technology, and that's kind of what we're thinking, like other human-like level of technological advancement sort of thing. Some of them see us only for a year or 2 years. They kind of skate our zone and then they leave. Others could stare at us for 10,000 years. Yeah, which is crazy. So
like one of those stars that you said where you might be headed right toward us or right away, they'd have a nice long time potentially to look at us.
Right.
Whereas one that had up,
Yeah, exactly.
Cool.
So isn't that wild? I think it's a really fun project to work on too, because we don't actually know as exoplanet scientists, and I'm kind of like a periphery exoplanet scientist. I didn't really say too much of what I did, but in the other cosmic conversations we did, I study low mass things. I study kind of like high mass exoplanets, but these transiting planets are tiny. A lot of them are like rocky worlds, or at least that's what we want. And from that perspective, we don't really think. We think about our snapshot in time of looking at these stars, but even the Earth might be exiting a transit viewing zone for another star very quickly, because we could just be missing some of the worlds that are out here.
Right.
So it's food for thought, as much for astronomers as it is for the general public, for your audience to think about it, man. When you look up at a star, twinkle, twinkle, does it have a planet around it? You might not be able to see that transiting world for very long. So
yeah.
Right
place at the right time.
It's all Goldilocks. Everything comes down to Goldilocks zones.
Well, very cool. Well, thanks again for joining us, Jackie, and I hope you enjoyed our cosmic conversation. We're going to take a break next week for the day after Thanksgiving, but we're going to post some greatest hits video at 11:30 next Friday, so you can look for that. Otherwise, we'll hope to see you on a future cosmic conversation, 11:30 Pacific, during the month of December on Fridays. And thanks again, Jackie.
Yay.
Have a great afternoon, and happy
Thanks,
Thanksgiving.
everybody.